Hi everyone. Welcome to ECO730. Today we are going to deal with the chapter on Granger causality. This concept of Granger causality really is sort of similar to the concept of which one comes first. Is it the chicken that comes first, or is it the egg? The egg and or egg and chicken thing that people talk about. So, but now, in econometrics, or even in economics, we always have situations whereby we always have an understanding that, say, for example, if we take an example of, say, growth and exports, some people basically argue that no, in order for um, growth to take place, there should be more exports, and then others are contending that no, or contesting that no, in order for exports to be more, growth is needed. So it sort of raises a question as to which one should come first or which one comes first. So therefore, this concept of Granger causality is really about the ability of one variable to be able to predict another, or the one variable to help predict one another. So now remember that causality is really in this context, it also involves uh, 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 the situation where we have to look at whether the past values of the one variable do affect the current value of the variable that is being modeled. So, for example, if we have two variables x and y, so we would want to know if say, for example, if um, x can help to predict y, or if y can help to predict x. Now, we can only do that by looking at the coefficients of x. So if we look at the past values of x, do they help explain, or do they help, or do they affect y? If they affect y, then it means that x does help in predicting y. Or if the past values of y do affect x, then we can say y does help in predicting x. So it's really about predictability or forecasting. All right. And so, therefore, having said that, we can also say that in a situation where the past values of the one variable affect the other, then we actually then know that the predictability is possible. But if we have a situation whereby, say, for instance, the past values of x do not affect y, then we can then say y is exogenous. Or if the past values of y do not affect x, then we can also define x as exogenous. So what we can also draw from here is that causality also helps in determining exogeneity, as to which variable is exogenous or not. Now, usually for us to be able to test whether or not there is causality, we can do it using the traditional way of following the F test, where we have to get the values and substitute them into the formula and then compare the calculated value with the critical values. As I have shown here on the slides, as you can see, usually you need two models, the restricted model and the unrestricted model, and then you have to use their sum of squared residuals to do the calculation. But what I can tell you now is that in nowadays we have software packages that are actually programmed with or built in with that type of test, so you don't have to go through the manual way of doing that calculation, and you actually see, as I will demonstrate that in the eViews video that you'll see later. Now, let us just look at this concept. So now, let us assume we have two variables, x and y. So usually we say, all right, x is explained by the past values of itself and the past values of y. And at the same time, y is also explained by the past values of x and also its own past value. So in order for us to determine whether or not there is causality, we have to look at the coefficients of for example, in the case of x, we have to look at the coefficient of the past value of y. So now what we know is that if the coefficient of the past value of y, if this coefficient, for example, is different from 0, and the coefficient of the past value of x itself is equal to 0, then we can basically then say y leads x. So meaning, actually, y does affect x. And then in the same manner, if we go to the y equation, if this coefficient, okay, if this coefficient of x is different from 0 and this coefficient of y is equal to 0, then we can actually say x leads y, or x does, cause y. Okay, so that's Granger cos y. So you can actually see that the reason why we are saying if this is equals to, if this is different from 0 and this one is equals to 0, is because we want to see how x affects y and not necessarily how the past value of y affects itself. So we are interested in the past value of the other variable more, how it affects the one, because that's where we see that we can actually determine that the one variable does affect the other. But now if we have a situation whereby, for example, if alpha 2I here, which is the coefficient of the past value of y, and 1I here, beta 1I, which is a coefficient of the past value of x. So if these two are simultaneously equals to 0, then it implies that there is no causality at all, because it actually tells you that that past value of y does not have an effect on x, and that past value of x does not have an effect on y. So hence there's no causality. But if it happens that these two coefficients are different from 0 simultaneously, then it actually tells you that there is a causal effect from both sides. So, and that's why, for example, in the first instance where we have x or y leading x, that is a unidirectional causality. And where we have again x leading y is a unidirectional causality. Where these ones are equal to 0, where the variables are independent, there's no causality. And here in a situation whereby these ones are both different from 0, we talk of bidirectional causality. So meaning there's feedback from both variables. Now, how do we estimate that? Estimating the Granger causality usually can be done in a number of ways. So the first situation is, obviously, you have to look at the order of integration. If the variables are integrated of order 0, so then that means that you can conduct the Granger causality in the simplest form. In other words, that Granger causality is actually similar to the pairwise correlation. So and so therefore, for as long as the variables are integrated of order 0, you simply just do the simple Granger causality. And again, I'll illustrate that in the video. And usually the output will look like this. And you have to look at the probability value and you compare it to level of significance, which is 0.05. So if, say, for example, in this instance we have 0.05, but obviously if we round this off, it will be 0.06, and that's why in this instance we actually have to reject the null hypothesis. So the null hypothesis is that there is Granger causality, or we can basically, like just like the way you have it here, or we can basically say the lag coefficients equals to 0, because if there's no causality, you are basically saying the coefficients of the lagged variables actually do not, equals to 0. So, and hence that past value does not affect the current value of that variable. And that's why, if that is the situation, then you actually then have to accept, you actually then have to accept that null hypothesis. If, in other words, if p value here is greater than the level of significance, you do not reject. But if the p-value is less than the level of significance, then you reject, because if you are rejecting that the lag coefficients are equal to 0, you're actually saying they are different from 0, and so therefore there is causality in that instance. So you can present the table in this manner, or you can present it in this manner, whereby you write the variable. This is, for example, inflation and exchange rate. So if we, for example, have to replace this with what we have here, so here we will have log GDP, here we'll have log M2 GDP, log GDP, log M2 GDP. So of course, log GDP with log GDP will be 0.00, but that value of 0.0056 will then go here, and then that value of 0.6274 will go here, and 00, because this will have then, for example, log M2 GDP, log M2 GDP. So you can present it in any of the two ways, but the interpretation remains as that. So the null hypothesis is that lag coefficients equals to 0. The alternative is that lag coefficients are different from 0. And so you accept and reject depending on what the probability value tells you. The second way, or the second instance where you need to, how you need to contact the Granger causality is if the variables are integrated of order 1 and there is no co-integration, then you have to actually do the Granger causality within the VAR framework or within the vector autoregressive. Because if you decide to estimate the Granger causality, the simple pairwise Granger causality when variables are integrated of order 1, then that will actually give meaningless results, because it will be more of spurious results, because the order of integration is different and you are actually using a different test, or a wrong method, which is only applicable to when variables are integrated of order 0. And I will again demonstrate that when we do the EViews demonstration. So, and that's why it's argued that if variables are integrated of order 1 or order 2 and they are not co-integrated, then you conduct the Granger causality within the VAR framework. And then lastly, we have a situation whereby if the variables are integrated of order 1 or order 2 and they are co-integrated, so meaning they have a long run relationship, then again it's inappropriate to do the simple Granger, but rather we have to do the Granger within the vector error correction model. And again, we will illustrate that in the EViews video. And so therefore these are the three ways in which you can actually conduct Granger causality. And within the vector error framework, actually you can even test for simultaneity. Okay, whether if all the variables are included simultaneously, because here you have in the VECM you have all the variables simultaneously included in the model, so you can test if that is the case. Okay, so, and that's why you see when you get the output from the VECM, and you can see here VEC Granger causality block exogeneity while test. So you have the individual variables. This was GDP against all other variables. This is public health expenditure, capital formation, age dependency, life expectancy, infant mortality rate. So this was a model. We were looking at how these variables affects growth, and so you then get the individual probability, and then you get the overall probability. Okay, so for example, here we can again see that it's here is a 50-50. It's a 50-50 in that 0.05 is equal to 0.05. So we cannot say there is no causality. At the same time, we cannot say there is causality. But probably you have to use your own discretion, because probably one could argue that if there was no causality at all, then this value would have been 0.05 something. So perhaps we could lean more towards of actually concluding that there is causality between um, GDP and all the variables jointly. Because if we look, okay, but again, now if we look at them individually, we can actually see that none of them, we can only see it's only life expectancy that would actually cause that, because 0.01, even if we round it off to 0.02, would eventually be less than 0.05. And so I think we are sort of leaning more towards that overall there is causality between GDP and all these jointly. So that is basically how you conduct causality given the three different ways. And I'll demonstrate that in the EViews video.